Today we're going to talk about t-distributions. So previously we learned that there are different situations where you use z and when you use t. And today we're going to talk about when to use z versus t. And then we're going to also break down and sort of reflect and recognize what is z and t, what do they have in common, and what's different about them. And for certain cases, we're going to ask the question, why not z? Why t instead? What doesn't z have? What's sort of deficient about z? And then we're going to talk about rules of t-distributions. They follow certain patterns. And t-distributions are a family of distributions separated by degrees of freedom. So different t-distributions have different degrees of freedom. So we're going to talk about what is degrees of freedom. And then we're going to talk about how degrees of freedom relates to that family of t-distributions. And then finally, summarize how to find t. Okay, so first off, when do we use z versus t? And we sort of covered it in previous sections where we looked at whether we knew the population parameters or not. In hypothesis testing, we frequently don't know the mu of the population, but sometimes we are given sigma, right, for some reason or another. And in this case, we use z in order to figure out how many standard errors away from the mean we are in our SDOM. But in other situations, we do not know what sigma is. And in that case, we use t in order to figure out how many standard errors away our x bar is from our mu. And just to draw that picture for you, remember, we're always interested in the SDOM because the SDOM tends to be normal given certain conditions. And although mu sub x bar equals mu, right, given the central limit theorem, what we often want to know is if we have an x bar that falls here, or an x bar that falls here, or a x bar that falls somewhere like here. We want to know how far away it is from the mu sub x bar. And in order to find that, we wouldn't just use the raw score and just get the raw distance, but we would want that distance in terms of standard deviation. But because this is the SDOM, we call that the standard error. So we would either want a z or a t. And these numbers tell us how many standard errors away we are from this point right in the middle, the mu. Okay, so what is z and t? Well, the commonality as we saw before, is it tells us the number of standard error away from mu sub x bar, right? And that's common to both. Right? And that's what the z and t score both have in common. And because of that, their formulas look very much the same. For instance, one way we could write the z formula is like this. Let me just write it here, let's see. So z equals we have x bar minus mu, right? Or mu sub x bar, they're the same. And this gives us the distance in terms of just the raw values, right? So just how many, whatever, inches away, points away, whatever it is, whatever your raw score means, degrees away, right? Divided by standard error, right? But if we sort of double click on that standard error and look at what's inside, then this standard error, also written as sigma sub x bar, because it's the standard deviation of a whole bunch of means, is equal to sigma divided by the square root of n, right? Now, if we look at the t-score formula, then we have almost the same formula, at least at first, right? We have that distance divided by how big your little steps are, how big your standard deviations are. But when we double click on this standard error, right, like something on a desktop, you double click it and open it up. What's inside? Well, you could also write this one as little s sub x bar. And that would be little s divided by the square root of n. And herein lies this difference right there. That's our difference. So here the difference is that standard error found using sigma, the true population standard deviation. And obviously, if you use the real deal, that's sort of better or more accurate. Then the standard error found using estimated population standard deviation, right? And that is S, right? And S is really estimated from the sample. And if we double-clicked on S, it would look like this. It's that basic idea of all the squared deviations away from x bar, right? Away from the mean of the sample. So x sub I minus x bar, right? Squared. We have all these squared deviations, and we add them up, right? Divided by not n, but n minus 1, because this is our estimate of the population standard deviation. And then all of that under the square root sign in order to just leave us with standard deviation rather than variance, right? And so this is an estimate of population standard deviation. It isn't the real deal, so it's not as accurate. So one thing you should know is that the z-score is less variable, and the t-score is going to be more variable. And that's going to come into bear on why we use which one. Okay, so why not z, right? When we have situations where we don't have the population standard deviation, why not z? Why can't we just be like, so you're using S, let's just use z anyway. Why can't we do that? Why be a stickler? Why do we have to use t? Well, it's because we use S. This is actually something a little bit weird. The weirdness comes from the fact that this S is much more variable than sigma. Sometimes when we get our estimate is spot on. But sometimes when we get our estimate is off, right? And that's what we mean by it's more variable. It's not going to hit the nail on the head every single time. It's going to vary in its accuracy. Now, z-scores are normally distributed when SDOM is normal. And here's sort of what this means. The way you could think about it is like this. When the SDOM is normal, and we pick a bunch of points out and find the standard error from those points and plot those, we will get another normal distribution. But that's not necessarily the case for S, okay? So here we need to know that z-scores are nice because z-scores are always going to give you it's going to perfectly cut up that normal distribution accurately for you. Because remember, the normal distribution, it always has that probability underneath the curve, and it has these little, marks, right? And these can be said in terms of z-scores, right? And what's nice about the SDOM when it's normal is that when we have the z-score, it'll perfectly match to the proportion of the curve that it covers, right? So this will always match, right? The problem is t-scores don't match up in this way. And so we can't just say, well, why don't we just call a z-score a t-score and then still use the same areas underneath the curve? Well, we can't do that. That's just a superficial change, right? Okay. And so here's what we mean by the z-scores are normally distributed. When you get z-scores and when we talk about normal distribution, I'm not just talking about that bell-shaped curve. Yes, overall it should have that bell-shaped general shape, right? But it's a little more specific than that. You could have the bell shape and have the perfect normal distribution. For instance, 1 standard deviation away will give you 30, this area will give you 34% of the area underneath the curve. This area is about 14% or 13.5%, and this area is about 2%, right? So that is a true normal distribution. Now this, on the other hand, it looks on the surface as if it's normally distributed. It looks like that bell-shaped curve, but it's not. Here's why. This area, it doesn't actually, so I should have actually drawn it a little bit differently, but I wanted to show you that don't go by appearances, Appearances can be deceiving. So this might actually be a little bit less than 34%. It might be something like 25%, right? And so if that was the case, you would see this area, right? And that area is not 34%, it's 25%. Not only that, but this area is now a little bit more than 13.5. It's around 14%. And now this area is not 2%, it's 11%, right? So although it looks like a bell-shaped curve, it's not quite a normal distribution because it doesn't follow that empirical rule that we had talked about from before. Now, what's nice about z-scores is that z-scores will always fall in this pattern. These z-scores will always correspond to these numbers. So that's why you could always use that z-table in the back and rely on it. But t-scores are not going to do that for you. T-scores may not give you that perfect 34, 13.5, 2% sort of distribution. Even though the S-stom might be normal, the t-scores are not necessarily normal, right? So we have a different, we have this normal thing, and then we have t-scores, and it's like, how do we go from t-scores to finding this area underneath this curve, right? That's the problem we have here. Well, it turns out that if n is really, really, really big, then this doesn't matter as much. If n is really large, if your sample size is large, then the t-distribution approximates normal. So it goes towards normal. But when n is small, then you have to worry, right? And also when n is in the middle, or when n isn't really big, it's just large, right? So it's like there's all these situations where you have to worry about the t as well as the area underneath the curve. So if the t-scores are not normally distributed, then we can't calculate this area underneath the curve, right? So if we have our lovely S-stom, right, and we know that the S-stom is nice and normal, right, and we have our x-bar here, mu sub x-bar here, everything's fine and dandy. We have, let's say, an x-bar here, and we want to find that distance, and we find the t-score, right? The problem is we can't translate from this directly into this area. That's the problem we run into. So, this may be a duplicate slide, but I'll use it anyway. So here, what we see is this is sort of more like a t-distribution than a z-distribution, right? And I'm just going to call these z-distributions to call them basically the normal distribution, right? The t-distribution is often a little bit smushed. Like, think of having that bell-shaped curve, that perfect normal bell-shaped curve, and sort of squishing the top of it down, right? It makes that shape sort of bow out a little bit, right? It's not as sharply peaked. It's a little bit more fat, right? A little bit more variable, right? And we had said the S is more variable than the sigma, right? And so it makes sense that the T that comes from S is more variable than the Z that comes from sigma, right? Okay. But you might be thinking, oh, great. So what are we, stuck? No, we're not stuck. Here's why. A guy named Gossett actually worked out all the T distributions as well. He went and this is like back in the day, so he manually calculated a lot of the T distributions and found tables, made tables of the T distribution that we still use today. He published those tables under the pseudonym The Student. At the time, he was working for Guinness Brewery, and he couldn't publish because they were sort of like, oh, we don't want you giving away our secrets to very dark beer. And so he published under the pseudonym, and because of that, some of your T distributions in the back of your book may be labeled The Student's T, to talk about Gossett's T. Now, here's what Gossett found. Gossett found that the T distributions can be reliable too. You could know about them. It's just that you need more information than you need for the Z distribution. For Z distribution, you don't need to know anything. You just need to know Z, and it'll give you the probability. That's it. Life is simple. T distributions are not that simple, but not that complicated either. They have a few more conditions to satisfy, and the biggest condition that you'll have to know is about degrees of freedom. Because for each degree of freedom, so degrees of freedom of 2, degrees of freedom of 3, of 4, of 5, and so on and so forth, there is a slightly different T distribution that goes along with it.